recording on. Okay.
Oh, I need to put continue. All right, so I'm going to give you today some introductory overview of dynamical mean field theory, beginner's guide, DMFT. Okay. So this is the outline of today's presentation. It's really introduction to DMFT, so I will start with kind of motivation. Why do we need dynamical mean field theory? And this is coming from the fact that many materials are correlated, and DMFT is one of the most successful theories for treating correlation in electron systems. Then I will discuss or outline how DMFT equations are constructed, just for educational purposes, and I will show one of the biggest success of DMFT in solving Hubbard model, and in particular in solving Hubbard model in the context of metal insulated transition. And I hope this introduction of DMFT will be like a starting point for other discussion of dynamical mean field theory, in particular for DMFT and Plus, which means DMFT in real materials or maybe other systems. Okay, so DMFT, dynamical mean field theory for strongly correlated electron systems. So I highlighted here correlated systems. So in general, correlations, what do you mean by correlation? So in general, it can be that the motion of correlated electrons, one electron is influenced by the presence of another electrons because they're interacting, right? And then in such case, the expectation value of some kind of density correlation function of electron at position R or R prime cannot be written as a product of the average of densities at some of electrons at position R or times the average density of electrons at position R prime, because of this correlations effect. And Hubbard Model insulator and double occupancy calculated in that sense will show you exactly what that means in that context. That will come a little bit later. So overall, what this equation wants to what information this equation wants to translate is that once you have correlations effect, induce beyond factorization effects, right? This means you cannot write this as a product of some average quantities, and this is what is employed in Hartree-Fock approximation. So you approximate some quantities as just some average quantities. Also, you cannot approximate correlated system or study correlated system as independent electron motion of independent electrons, because obviously the motion is really correlated. And basically, for correlated systems, the main message is that one body independent electron theory breakdown. And correlations, it's not just some phenomena which is common for correlated electrons. It's actually common for many systems, including humans, right? When humans interact or interact, different behavior can emerge, and it's present in physics, chemistry, biology. And this was pointed by a famous Anderson paper, More is Different, where he was showing that because of correlations, different emergent behavior can appear, where new phenomena appear from many objects which interacts, and it's fundamentally different from the motion of independent objects. Okay, so what are the correlations effect in strongly correlated electron systems? So when we have correlations for strongly correlated electron systems, they can lead to some subtle interplay between different degrees of freedom. This includes charge, orbital spin, and lattice degrees of freedom, and that in turn can give rise to a very exotic states of matter. One example of this is, of course, superconductivity in high temperature superconductors. It can lead to different types of ordering, for example, orbital ordering or charge ordering or magnetic ordering. And overall, it can lead to very complex phase diagrams, and can be exemplified by the phase diagram of cuprate, which has these different colors corresponds to different phases of matter, all right? And what is also very interesting for correlated electron systems, properties of these materials, the phases of these materials and properties of these materials. Unlike simple metals or insulators, the properties of these materials are strongly depends very sensitive to external perturbation. So you can manipulate their properties by changing like temperature, doping, magnetic field, what else, pressure, and you can induce very strong dramatic changes in, for example, in conductivity or resistivity. It can lead to, for example, one of the most famous phenomena is like mode metal insulated transition. Okay, so correlated electron system actually present a big chunk of materials in periodic systems. So these are usually materials with open DNF bands, with partially filled narrow DNF bands. So this include transition metal oxides. And here I put some examples, like the most common, the canonical example, I think, which goes back into 30s or 40s, is metal insulated transition in nickel oxides, iron oxides, V2O3 systems, transition metal peroxides, cuprates, superconductors, manganites. These are all strongly correlated systems. Also, strong correlations are found in actinides and lanthanides, and I show some examples here. And of course, the most famous examples include heavy fermion compound exhibiting Kondo effects. So in these materials, spatial confinement of electrons at narrow DNF bands enhances the effect of Coulomb interactions, making these materials strongly correlated. Okay, now one of the most fundamental phenomena seen in strongly correlated electron system is, of course, mode Hubbard metal insulated transition. And it has been seen in variety of correlated materials. And I show here the phase diagram for some of them. So this includes the canonical example on metal insulated transition in transition metal oxides V2O3 samples, where about at elevated temperature above antiferromagnetic insulator, mode metal insulated transition, insulated to metal, can be driven by, for example, pressure, or it can be driven by temperature. Also, what happened? I don't know. Sorry about that. Also, mode metal insulated transition has been seen in 2D organic kappa salts, and this is shown in this shaded region here. The shaded region corresponds to the fact that metal insulated transition is actually a first order transition. So there is some coexistent region which is depicted by this shaded area here. Also, mode insulator is a parent compound of high temperature superconductors. So the discovery of high temperature superconductors in 80s, right, ignited yet another interest in understanding and solving a mode insulator problem. And finally, mode insulator can be also found in strontium rutenides, shown here in this part of the phase diagram. So what has been the challenge? The challenge is that at that time, how do we distinguish between metal and insulated transition? So we use the band theory of solids. This is what we learn in the textbook, right? Where metal and insulators are distinguished by the absence or the presence of the gap in the density of states and depend on the filling of the band. So the canonical examples of the failure of the problem which shows that we have a problem for correlated system using the band theory of solids, which employs independent electron approximation, is where the materials, nickel oxides materials, which have partially filled D bands. So according to the band theory, they would be metals. However, experiments are shown here. This is experiment shows there is actually a very wide gap in these materials, which band theory of solid obviously is not able to capture, because it employs it employs independent electron motion, which I have mentioned before is not appropriate for description of correlated system. And then DMFT came into play in 1989 and 1992, and one of the biggest success of DMFT was a solution of Hubbard model, and solution where one can show the metal insulated transition, proper description of the metal insulated transition. So this is the Hubbard model the Hubbard model Hamiltonian, and Camille has done a nice introduction on Hubbard model in the 2 weeks ago. So, and just to remind ourselves, so it consists of 2 terms: kinetic energy term, which describes the hopping of electrons between different sites. And in Hubbard model, we make approximations. We say that electrons are fully screened. So the potential interaction, potential energy, which described by this term, is a Hubbard U term. It only describes the interaction of electrons when they meet at a given site. Right, that's why we have an I up and I down. So only electrons, when they meet at a given site I, this is the only time they interact, but they have to have a different spins up and down to satisfy the Pauli exclusion principle. So Hubbard model seems to be very simple. But it can be solved only exactly in 1 dimension, and also in infinite dimension using DMFT. But in general, it's really intractable problem under perturbation expansion. But this is a minimal model that can describe the competition between kinetic and potential energy terms as a driving mechanism for metal insulated transition. So DMFT is another limit when Hubbard model can be solved in infinite dimension, can be solved exactly. So now I naturally I'm going to discuss how DMFT was constructed. So okay, so dynamical mean field theory. So that's the reason I put the slide here. So there is some keyword here, mean field, and we have to be a little bit careful about this. So, but let me just remind ourselves what do we mean by mean field approximation approach. So the best way to introduce DMFT is to draw analogy between the static always mean field theory, which we all learn in our static mechanics course, and this describes if applied for the Ising model, right? So here on this on the left side here we have the Ising model. So we have interacting spins at different sides I and J, and there is coupling between them J, and these spins are placed in some effective field H. Okay, well, this is many body problem, but which is hard to solve. Instead of solving this problem, we can use mean field approximation, which employs a mapping of the lattice problem to the impurity problem embedded in effective mean field. Okay, so instead of solving this Hamiltonian, we can decouple spin-spin interaction by writing H effective Hamiltonian, which is considers interaction of the spin with some effective magnetic field created by the rest of the lattice. Right, this is H effective represents the overall effect of the rest of the lattice on the given spin. And this effective magnetic field H effective, this is what we call Weiss effective field, is constructed by summation of the rest of the other sides except for the side I, you can say that. Doing this mapping, one can also come up with the self-consistency condition for determining the magnetization in this effective field. So this approximation becomes exact in the infinite dimension limit, and we solve it just by doing the self-consistency iteration.
I have a question.
Yes.
By infinite dimension, you mean the infinite number of neighbor sides.
You can say infinite coordination number, that's true.
Okay.
Yes,
thank you.
but Z here is a coordination number. But also, please, I want to point out here that there will be a big difference between dynamical mean field theory and this Weiss mean field. Here, Weiss mean field, this H effective, is just a number. It's not a function, it's just a number which represents the overall effect, average effect of the rest of the sites on a given site spin SI. Now let's turn this. Let's now turn to the dynamical mean field theory. So a little bit of history. So since Hubbard model in general is intractable problem, so mean field solution usually provides some kind of insight. Can provide some kind of insight. So from that perspective, Messner and Wolhard considered infinite dimension limit for the Hubbard model, and they have found that in infinite dimension limit or infinite coordination number Z limit, equation for the Hubbard model can be simplified, and one can get non-trivial solution if one does some rescaling. In their case, it was hoping term T by coordination number. So one would get some non-trivial solution in that case. Later, and at that time, Mueller and Hartmann have shown that in this infinite dimension limit, the self-energy is actually local for the Hubbard model. And that led to the further development, which were brought up by Antoine Georges and Gabi Kotler, that in exploring the fact that self-energy in infinite dimension limit is local, they have shown that the Hubbard model, the lattice Hubbard model problem can be mapped into the quantum impurity problem embedded in effective medium. So that was a big breakthrough at that time. And then Mark has also contributed to solving this quantum impurity problem using quantum Monte Carlo method. Okay, before I go to and show you the mapping from the lattice problem to the quantum impurity problem, I want to mention that DMFT is the Green's function method, and Green's function. So I'm going to make a very short overview, a little bit of Green's function. So Green's function is the object which describes the propagation of electrons through your lattice, and it's given by it's defined in this way. So it has a position or side index and time index. So if we go do Fourier transform, and that's what I will be presenting data for Fourier transform. So it has momentum index and frequency index. Okay, one can also write the fundamental equation for Green's function as Dyson equation, which is G, this is full or interacting Green function, can be expressed as non-interacting Green function G0 plus G0 sigma G. Sigma is very fundamental quantity here because it's a self-energy, and it incorporates the all correlations effect on a given electron, which is propagating into the sample. So sigma carries the information how electrons are interacting and correlated between each other. Okay, why Green's function? Green's function is actually a very nice tool to do some calculation which can be compared with the quantities that can be measured experimentally. For example, one can calculate density of states, and I'll be showing the results for this, as -1 over pi imaginary part of the local Green's function. Okay, and this can be measured by photoemission spectra or STM. Okay, we can also calculate the momentum result spectral function, which is just minus imaginary 1 on a pi, imaginary part of the momentum result Green's function, and this can be measured by RPS, for example. One can also calculate using Green's function method some response function like conductivity or resistivity and compare this with the experiment. Okay, so now let me outline the main steps which have been used to construct DMFT dynamical mean field theory equations. So, so the quantity of interest, as I mentioned before, is the Green's function. And to calculate Green's function, we will be using this path integral formulation. And for that, we have to calculate the effective action S. Okay, so this is the effective action S, which corresponds to the original Hubbard model. Okay, you have Hubbard U term and you have Hopin term T. But then what our goal is to map, like we did in a static mean field, to map the lattice quantity into the impurity embedded in effective medium. To accomplish this, we break this lattice effective, we break the lattice action S into, we can just write down, separate the terms. S0, this is action for the site, this impurity site S0. So it contains the interaction at a given site 0, or we call it cavity, you can call it also cavity, then there will be term which describes the hopping from site 0 to other sites in the effective medium. This is this term. And there will be other term which don't include site 0 in the summation. So this is the rest of the lattice. Okay, then one can formally integrate out of this the rest of the lattice. So this S sub 0 superscript 0 of action. Okay, as a result of this formal integration, you will get the Green's function superscript 0, right? This shows that this you integrated out over the rest of the lattice except for this impurity 0. And then you will arrive in this as effective action as effective, which looks like this. In infinite dimension limit, one can show that these 3 dots here will disappear, and what you will be left with will be the action of quantum impurity problem. The quantum impurity plays in this effective medium, which we call, which described by this G script 0, which plays the same role as a Weiss field in the static mean field theory. So this is the main equation here. So we are going from this lattice action to the quantum impurity action, where we have impurity part here and the Weiss field, which represent the rest of the lattice effect on this impurity in a dynamic way. Because unlike in the static mean field theory, the Weiss field, this G script 0, it's not a number, it's a function of frequency. That's why we call it dynamical mean field theory. Now the rest is simple, right? Because now instead of solving this problem, you are solving this quantum impurity problem, which is described by this action. And as a result of this, you can get the impurity Green's function. So this is coming from this action, because when you do quantum integration of interactions, this will give you self-energy term, and you have this Weiss field here, okay? And this is not the end of the story, because you can solve impurity problem, but these things have to be determined self-consistently. So self-consistency requires that impurity Green's function is the same as the local Green's function of the original lattice, okay? And this is the equation for the lattice Green function. Since things are local, self-energy doesn't have momentum dependence. And here you just have to sum up over K, because you want to make the thing local. All right, so there were too many equations, but in a nutshell, what we have done, we have reduced the intractable interacting original lattice problem into the quantum impurity problem. So we have impurity placed in effective medium, dynamic medium, okay? In dynamical mean field theory, what we have done, we see that this effective medium and self-energy, they are only function of T or frequency. So they are dynamic quantities, but they are not function of momenta. So we neglected spatial fluctuation, and as a result, we map our problem from lattice to impurity, and that impurity problem is now described by this effective action. And our goal is to just to calculate the impurity of this impurity effective action. And again, please notice that in dynamical mean field theory, the effective field is not a static quantity, is a function of time, which allows, this has an important effect on results, because it allows the electron to come from the base or come back, go back to the base. But at some point, this graph here shows that the occupancy of the impurity site can be either empty, you can have one site, it can be singly occupied with the electron will spin up, or it can be spin down, but at some point you will have the 2 electrons can come from the base and occupy the impurity, and this is when you will be testing this correlations effect at a given site. Okay, and this slide is just to show you some similarities between static mean field and quantum impurity case. So, so this is Hamiltonian, this is Hubbard Hamiltonian. For a static mean field, you construct the effective Hamiltonian, where you can see the spin embedded in effective mean field. Here you construct the effective action, but again, you can do this mapping and construct the corresponding impurity action. And then the quantity of interest for Eisen case is magnetization. For Hubbard case, you calculate impurity Green's function, but again, things have to be self-consistently determined. So self-consistency condition requires that impurity Green's function for this given effective field is the same as the local lattice Green function for the which is function for of a given effective mean Weiss field. And again, the difference is that static for Eisen case or classical mean field approximation, effective medium is described by static mean field, and for dynamical mean field theory, it's a dynamical quantity which depends on the time. So basically, you free spatial fluctuation, we don't have any k dependence, but a dynamical fluctuation are taken into account exactly. Okay, so how do we proceed after that? After that, we solve DMFT equations iteratively. So the main, the most difficult part is actually, a time-consuming part is to solve the impurity problem. And again, you have to solve this effective impurity corresponding to this effective action. From by solving this impurity problem, you get the impurity Green's function. Then you can use the Dyson equation to extract the self-energy. Then you plug this into the equation how to calculate the local lattice Green's function. So this goes here. And then once you have this, you can calculate a new Weiss field, which you need as an input for the to define your impurity problem. And this can be calculated using, again, Dyson equation, but now you're using the local lattice Green's function. And you do this iteratively until things converge, so until you get that impurity Green's function is equal to the local lattice Green's function. Okay, there has been, I just want to point out this one, that one of the things that had led to DMFT being highly used in the community at that time was that it has been realized that the effective impurity action that we have seen before is actually the same as effective action of the single impurity Anderson model. And this is single impurity Anderson model. This is a model that has been used to study Kondo problem. And at that time, it has been very widely investigated. And so the problem when you have magnetic impurity placed in the non-interacting conduction electron bath. And at that time, there have been many impurity solvers available for single impurity Anderson model. So that led to further development and progress in solving DMFT equation for Hubbard model. So, so now we have different impurity solvers. These include quantum Monte Carlo method, diagonalization, NRG, DMRG, iteration perturbation theory, and etc. I also want to point out this slide this slide where I want to point out the similarities between DMFT self-consistency equations and the CPA equations for disordered systems. This goes back to several weeks presentation ago where we discussed CPA. But basically, as you can see from the slide, solving CPA for non-interacting system is very similar as solving DMFT for interacting system. The only difference is that you're solving a different impurity problem. Okay, but the rest self-consistency condition and self-consistency equations, the iteration equations in the numerical iteration group are the same. Okay, so the only difference is a different impurity problem you are solving. Okay, so now let's go back to the mode transition and see how DMFT can be used to solve this. Before I go to DMFT results, I would like to present some experimental feature of mode metal insulator transition. So the canonical example to study mode metal insulator transition was V2O3 materials, where it has been shown that Mode metal insulated transition in this system is temperature pressure. It can be driven by pressure or temperature, and it is a first order metal insulated transition. So there is, you see, there is a shaded region which corresponds to this coexistence region, and over this region you would have what you usually see for the first order transition behavior, that you will see this hysteresis behavior. And this can be better demonstrated at this graph, where you show conductance as function of pressure and temperature. So for low temperature, we can go from metal to insulator as we decrease pressure. And so as you decrease pressure, there is a huge jump and system become insulating. So this sharp changes, abrupt changes in the conductance or resistivity, these are characteristic features for first order transition, but also hysteresis behavior is characteristic for this. So if you go now back, increase pressure, you will see that you go from insulator and to metal, and there is this coexistence region. So this plane here is just basically this plane here, this graph here. So in this plane, you could find two solutions basically if you do DMFT solution. And if you increase temperature, right, this coexistence region is better seen here. It shrinks until you get to the finite critical point you see, above which the transition becomes a second order and becomes continuous. So first feature is the first order transition. Second, it has been shown that correlated metals, so close to the transition, there is a characteristic 3-peak structure in the density of states. Okay. So let me first show the results for a dynamical mean field solution for the mode insulator, and we will go through the evolution of the density of states at different values of a ratio of U to the bandwidth. So we start with a small ratio of U over a bandwidth. So we are mimicking these pressure effects. So it's small interactions, right? We have a metal, and at very large interaction, we have a mode insulator, which is characterized by the opening of the gap in the density of states. And now let's see, let's take a closer look how we go from metal to insulator. So we see as we increase interaction U over D ratio, there is this characteristic 3-peak structure developing in the density of states. So at Fermi energy, we have this quasi-particle coherent peak, which as we increase interaction U becomes narrower and narrower. And at the same time, the weight from this quasi-particle peak will be transferred to the lower and Hubbard bands. So we have a transfer of the weight from the central peak to the incoherent lower and upper Hubbard bands. And the transition will be characterized by the disappearance of this quasi-particle central peak, which corresponds to so the width of the peak can be described as Z, and this is 1 over Z is proportional to effective mass. So you can say as you approach the transition, quasi-particle disappear and effective mass is increased due to the interaction is increased. Such transfer of the spectral weight from the central peak to the Hubbard subband has been actually seen experimentally in 1992 in a series of transition metal oxides, and it's shown here. So experimental data are with these squares, and band theory is this with solid lines. So you can see only for very, very weakly, basically non-interacting systems, band theory is good. But once you increase interaction, you see, so these lines here, this is close to Fermi energy. This shows the coherent part of the spectrum, and this part is incoherent or Hubbard subbands part of the spectrum. But we see that there is a transfer of the weight transfer from the coherent peaks to the incoherent part of the spectrum, similar to what we have seen here in DMFT picture. Also, we can see that this correlated metal, right, once U are increased, has this characteristic 3-peak structure. This has been seen in experiments too. So this is a data showing in squares. This is again experiment, and again this is a half of the spectrum. So you have two of them, you will have three peak structure visible. So this is shown for different energies. So for higher energies, when you can sample actually bulk properties, you can see this characteristic three peak structure. However, if you have lower energy, you basically sample the surface effects. So this three peak structure is not that pronounced. But anyway, it shows here that characteristic three peak structure in V2O3 materials as well. These are more recent calculations, and these are on different correlated metals. And these were done calculation by LDA plus DMFT and compared with experiments. And they also show that for correlated system, one has this quasi-particle peak and Hubbard subbands forming this three peak structure. And this behavior is completely missed in, for example, Hartree-Fock approximation. And now one can do this analysis, this metal insulator transition analysis for different temperatures, do this systematically for different temperatures in interaction, and one can construct temperature interaction phase diagram. So, and this is what we see. For small interaction, we see metal, and for large interaction, we see insulator. We have this UC1 and UC2 lines, which delineate the region of the coexistence region. So in this coexistence region, if you go from a metal, we will have metal solution, metals, we will find the metallic solution up to this point, up to this spinodal, and after that system become insulator. When we go this way, if you start from insulating solution, we will have insulating solution up to this point, and the system become a metal. So in this coexistence region, we could have different solution depending which initial solution we will be used in our analysis. So this is the coexistence region that I described, because this delineates the region of the first order transition. As you increase temperature as expected, that coexistence regions is getting narrower and narrower. And it ends up in the second order critical point TC. Another feature of correlation-driven feature that this is correlation-driven metal insulator transition is to calculate this quasi-particle peak Z as function of U. So we expect that quasi-particle peak of quasi-particles will disappear as you go to insulator. So quasi-particle peak disappears as you turns into the insulator. And again, quasi-particles related to is inversely proportional to effective mass. So this will be also signaling that once you correlations interactions are increased, electrons behave like more heavier particles. And another feature to show that there are some localization effect happening to interactions, a large interaction U, is to calculate double occupancy. Right, this density correlation at a given site I. We see that double occupancy is getting suppressed as you increase interaction U. And this picture just shows you that if you have very large U, you get to the mode insulating regime, electron would not like to hop from one site to another, because if you have two electrons at the given site, it will cost you energy U to have them there. So instead, they will prefer to just localize at the different sites. Okay, I will just highlight, quickly describe this. So what we have done with Vlad, we explored not a smaller temperature regime on the phase diagram. We also look at the higher temperature regime of the phase diagram, and that was driven by the motivation that the critical temperature TC for this second order TC of the second order TC point is very small. It's only 2% of Fermi energy. So we were interested if there is anything else in this high temperature regime, and in particular, we were looking for some evidence of the quantum criticals, of some hidden quantum critical behavior in the system. In particular, we have found that in this high temperature regime, the resistivity data, we calculated the resistivity data, and we have found that resistivity data in this high temperature regime over this range highlighted area can be scaled into insulating and metallic branches. And the scaling that we have found for this regime is characteristic for quantum critical scaling. I will not go to these details, but I'll just show you that these analyses have been also explored experimentally. The analysis of this high temperature regime above second order mod metal insulated transition have been explored experimentally in several materials. And it has been found that the high temperature mod quantum critical crossover seems to be ubiquitous feature for system exhibiting mod metal insulated transition. And one can ask, is DMFT, because DMFT employs local approximations, so cell energy is local, it's not momentum dependent, and one can say, is this enough? It turns out that for some system it's not enough. For example, if you want to study superconductivity in cuprates, one has to go and include momentum dependence of self-energy, and this can be done in multiple ways. And one of the simple ways is to do cluster extension of DMFT. So you place a class instead of impurity, you place cluster in effective medium. And there are two ways you can do this. You can do this in momentum space, that's what we know DCA, or you can do this like a real cluster in effective medium. So this is cluster DMFT. Okay, but in this case, as you increase system size, cluster size, you will approach some exact solution, because there is a small parameter 1 over cluster size, and within the cluster, you will be capturing systematically some momentum, recovering some momentum dependence of the self-energy and Green's function quantities. And this is my last slide. So this is just to show you that there have been a lot of progress of exploring DMFT in other aspects and extending DMFT to other aspects of strongly correlated systems. So I call it DMFT Plus. So one of the things that we would be interested in hearing, for example, next time or some other time, is how DMFT can be combined with real materials. So the first combination by DFT plus DMFT, LDA plus DMFT, GW plus DMFT, and there have been a numerous group in United States and outside in Europe working on this. And I pointed out some references here and some beautiful slides where you can find good information about this. Also, DMFT has been extended to non-equilibrium systems. So this is reference here, and DMFT can be used to some heterostructures. I think Thomas is also exploring heterostructures and other much more complicated system beyond single site Hubbard model, single band Hubbard model. So with this, I finish. So this is my small introduction of DMFT to you guys.
Oh, thank you. It's a very nice talk.
Thank you so much.
Yeah. So let's ask the questions. Okay, I'll ask first. So obviously, in your DMFT solution, that there's from the calculation you're going to run, seems like still depend on this U. You still have like a Hubbard model U.
Yes.
So what do you have? How do you get U to begin with?
Oh, it's just a parameter for us.
It's a parameter.
It's just a parameter.
Okay. So for the expect, so when we have like a DMFT combined with the LDA method,
yes,
DFT method, then we still have to determine what U is.
Yes, but I think that one is determined from this LDA, for example, calculations.
So that it basically is very similar. I mean, problem to if you do LDA plus U.
Yes.
So most practitioners get the U from experience. For that material, you use that value of U, and I mean, you run calculations for a range of U's and see which value of U produces the physics, which is a nice interpretive tool, but it unfortunately somewhat defeats the purist ab initio view of we would like to have if we do a DFT calculation. I think that there are, I mean, there are some ways on how you can calculate that. I'm trying to remember, but that's not very widespread. I mean, the standard approach really is you use it as an additional parameter in your theory, which you have to
compare with experiment.
have to fit to reality.
So to add with Marcus' comment, so generally people can calculate U from constant LDA.
Yes, yeah, the constraint.
Yes,
yeah, but,
I don't have any experience. I never calculated. I just heard and got in from
yeah,
it.
but that is actually, I mean, usually the answer you get for that question, but it's very rare that people actually do that.
Yeah, okay. Even in LDA plus DMFT method, also people use this U as a parameter.
Yeah.
Okay.
And we have an expert in this. We have Livu and his postdoc, right, Andres? Maybe they can give us a talk on this. So.
Okay. So obviously you only show the single band. In the case like things get complicated, we have to have like a multi-bands.
Yes.
So DMFT, I guess, will still apply.
Yes.
Then you're gonna have to apply DMFT to different different orbitals.
Yes, that's a very good question. So yes, there has been extension of DMFT to multi-orbital systems, and I should have included this. And in fact, there was some kind of orbital selective mode transition even identified. But as extension of DMFT to multi-orbital has been extremely useful recently with the discovery of iron-based superconductors.
Okay.
But it has been found there that Hund's coupling plays important roles, and you have this Hund's metal and etc. in these materials. But it was also found that within DMFT that you would have mode insulator for inter-J band fillings.
Okay.
And also with multiple number of bands, you have to also take care multiple number of basis atoms in your unit cell. In such cases, situation becomes really complicated.
So you're gonna have a dynamic mean field for each band for each orbital, right?
Yes.
Okay.
Well, what I've been told is that normally you can take bands from DFT and you can present them with some local basis using maybe Vannier functions. Then you get many local orbitals, but you don't need to actually consider the interactions in all of them, because if you put in a large interaction in orbitals which are nearly doubly occupied or nearly empty, then the impact of these interactions is negligible. But only a few orbitals which are nearly half-filled are really affected. And this is why these people who, practitioners of LDA plus DMFT and similar methods, they actually select through some projection method a very modest number of orbitals which are considered as correlated, where they put an interaction U or J, and then all the other orbitals or bands are treated as non-interacting, which is a huge simplification, because at the end you have to solve few impurity models with only few orbitals. And that's, I think, how many people have been dealing with this. My understanding is that this issue of constrained RPA and so forth has to do mostly with the fact that if you can imagine, you put a second electron in an atom which is neutral, now it becomes charged. And this charged atom will create an electrostatic field, but that will affect not only those bands near the Fermi energy, but many other bands, and they will create some polarization, which can partially, through dielectric screening, screen the interaction U or reduce the effect of this on-site repulsion. And that is apparently much more important in itinerant systems like iron-based superconductors than in cuprates, for example. And so this is a very non-trivial issue, I think. And as Marcus mentioned, there are people who do constrained LDA or constrained RPA, or I heard that now there are actually people starting to work on constrained LDA plus DMFT, in fact. Or, there is actually some evolution of this, but it's my impression that this is not completely understood. Now, I have actually been recently involved in a collaboration involving actually Christian Howley and some others under materials under extreme conditions. This was motivated by the fact that my own son is an experimentalist working in geophysics, and they go to pressures of hundreds of gigapascals, where the volume changes considerably, and temperatures of thousands of Kelvin. And what appeared, so we actually looked at structure. If you fix a U, you determine U, for example, by comparing your results at ambient pressure to some experiments, right? So you can vary U to get an equilibrium volume correctly, for example, right? Now you can ask, if you take that U and then go to extremely high pressures, where the volume is much smaller, maybe 20% smaller, these are huge changes. Then what do we get with the same U? And as it turns out, it is not working very well, in the sense that apparently if you go to extreme conditions, then this U or J, they have to be readjusted. And this is not important if you go to small volume changes or small pressures near ambient conditions, but under extreme conditions, this cannot be neglected, and apparently will affect, for example, the structure, unit cell geometry or polymorphism quite a bit. And so I think this seems like this is somehow, now for those, I've been under a lot of pressure from these people that I'm collaborating with in geology, the geophysics department. They are very interested in the equation of state, how the lattice volume depends on pressure. And then they would like to have some first principle calculation of this, which is accurate within less than 1%. Okay. But this is really difficult, and it doesn't work very well when you fix a U. So that was my personal experience, and I think it makes sense, right? That if you apply, say, kilopascals or something, it's not so important. But if you go to these extreme conditions, which could also be important, for example, for these actinides, and when people talk plutonium, the nuclear fuels, and all these things, there are some extreme conditions that are relevant to them.
that. It's now quite a while ago that Gabi and Kotler and so published their first paper on plutonium, and actually they are still working on that. So if you look at the recent InSight allocation that they've just won, is still looking at getting plutonium, which is a really tricky material, right?
Actually, my next question is about the pressure. So in that in the Hubbard model, in the DMFT, where I don't see the pressure. I know, but they finally draw pictures about pressure. But where the pressure coming into the actual calculation?
Because when you apply the pressure, you will change the ratio of U over bandwidth. So in Hubbard model, this pressure is modeled by the change in the U over bandwidth ratio.
Okay.
Yes.
So you have like quantitatively how you make you have a way to make a connection between pressure and then the ratio.
Yes.
Okay.
You can compute the energy. If you do first principle computations, you can compute the pressure or your energy.
Yeah, I take the
derivative as a function of volume. Yes, and you take the derivative. This is routinely done. This is how we've done actually the equation of state, and with some mixed results. I mean, it's not. For example, if for example, FEO that we worked on has various phase transitions between different structures. Rock salt at ambient pressure, at high pressure, there's a nickel arsenic structure, and some other structure, rhombohedral structure. And now, if you want to know exactly what is the pressure where this happens, what is the jump, is there a volume collapse? Those things are very, very tricky, and they require. So I think after many discussions, especially with Christian, we arrived at the conclusion that probably once you go to the metallic side, then it looks like maybe metallic screening is enhanced, and actually the effective value of U that you need to use if you have a first order transition between structures, maybe there is a jump. So it's really not a trivial question. How, if you are really interested in predictive power in terms of structure, these extreme conditions, this is very
Yeah, I fully
very
agree.
famous, very famous example is actually cerium.
Yeah.
Where you have, actually it's an isostructural transition. That is, the crystal structure does not change, but there is a transition in the electronic state that leads to a volume collapse.
Yeah, I'm sure the all those physics in the normal condition being explored fully, right? But there's a large space that hasn't been explored yet to the extreme conditions, high temperature, high pressure, and under those conditions, like a normal ambulatory method, like a pseudopotential method, will fail.
Oh yeah, yeah.
Pressure.
That definitely is somewhere where you want to have an all electron.
Yeah, only all electron method will work. The KKR method is a very ideal tool to do that kind of problem.
And I can tell you that I've been involved in this geophysics business because of my son. Most of the community in this area, they don't know about correlations, even though, well, in the mantle, you have mostly band insulators, except for iron and nickel containing compounds. Most of them are alloys. And one of the issues actually that may be interesting for this group is that they're very interested, for example, they have FeO. And then, iron is very rich close to the core. Core is iron.
Yeah.
There's a lot of oxygen in the mantle.
Yeah.
And one of the main components of the mantle is magnesium oxide, which is band insulated. So if you're going away from the core, you have there are actually regions which have abundant FeO, but then Fe is replaced by magnesium. And one of the things that are very important is that when you actually dope, so you have an alloy where you have a substituting iron by magnesium, then how does that affect the equation of state and the phase diagram? There are metal insulator transitions, and how are the critical pressures changing? That is very, very important for the convection of the mantle. And also, it is possible that some impurities, like their iron, they say that iron monoxide is very sensitive to iron impurities, iron vacancies. I'm sorry. These can help the system as well. And now the question is, for example, how we were talking about charge transfer. What is the stability or the entropy of these impurities at these high temperatures? What is the energetics of introducing these impurities, and how, so this is actually very, very important for the convection in the mantle. They are just starting to explore it. I think to answer those questions fully, we'll need some capability of the kind that you guys are trying to build, which is having a first ab initio description of materials, but also of impurities, because they probably play a big role. And there is apparently, there is definitely a large amount of charge transfer once you dope with these impurities. And how is that actually affecting the phase diagram? That's, I think, extremely important. And my impression is, for funding and so forth, that this area of extreme conditions and geophysics, that's actually, there are not so many people. There is a Russian group with Leonov and Anisimov who are doing some work on it. But I think there's a lot of many different materials and a lot of demand for theory modeling. People are skeptical, and a lot of them don't even know what correlations mean or what DFT means. So I think actually that's sort of a nice direction to think about, because a lot of the topics that I've heard you guys discussing, I think, are of great relevance for geophysics. And now the experiments that can reach those pressures and temperatures, they have started to appear recently. So they can now go to about 200. So this is actually,
there will be a lot of exotic phase diagram in that region.
So for the pressure, DMFT people follows like, we are considering unit cell, and we can change the lattice parameter and first calculate basic electronic structure of that material. So when you see, for example, density of states for different pressure, width will decrease. So for the different pressure, we'll have a different density of states of different bandwidth. So then we supply this information of density of states to the DMFT. So this way, DMFT take care of pressure.
Let me stop the recording, so then we can talk whatever we like, because this is going to be posted on YouTube. Is okay, Vlad? You will show up on YouTube. It's okay.
When I teach, I always say I always wanted to be a rock star, but it
getting
didn't work out,
right?
right?
Okay, I'm going to stop recording for now.